What is gravity? Commonly, we think of gravity as some magical force that pulls massive objects together. But is this accurate? Einstein showed us that this view, while a good approximation, really isn't the whole story. He showed that space and time are connected in what is commonly called the fabric of space-time. This is simpler than it initially seems. If you want to meet your friends to work on an astronomy project, you must specify both a location so everyone knows where to meet, and a time so everyone knows when to be there. If you say to meet at your house, your friends wouldn't know if they were supposed to come in an hour or in 2 weeks. Likewise, if you specify to meet at 7:30 tomorrow, but don't say where, your friends may assume you intend to meet in France and frantically attempt to book a flight. In this same way, space has 3 spatial dimensions and 1 time dimension that need to be established for a physical system. Einstein described gravity as the bending of spacetime. This is the theory referred to as General Relativity. More massive objects create a more substantial bend in spacetime, while less massive objects can cause little or no change at all. A lighter object orbiting a heavier one can be imagined to be following the curvature of spacetime created by the heavy object. Just as the curvature of spacetime can alter the path of planets, it can alter the path of light, causing light to bend and changing its motion. Look up at the night sky. Hidden in the constellation Ursa Minor is the Little Dipper, and on the end of its handle you'll find one very bright star named Polaris, the North Star. For thousands of years, humans have watched the stars, but for explorers, mathematicians, and astronomers, this star has had a particularly significant impact on our understanding of the night sky. With complicated machinery, we can measure a lot about this little star. The star is very bright compared to many of the others we see, and is moving towards us at a blinding speed. Now, suppose we hop into a teleporting phone booth that we borrowed, and ride it instantaneously into an orbit around Polaris. If you had good eyes, the first thing you'd notice is that Polaris looks less blue than it did on Earth. Looking past the fact that the star is bright enough to burn your eyes, something about the color of it has changed when all we did was move our position. This is weird. Does the color of your shirt change just because you move towards or away from it? No, but why is that what we observe here? Well, it has to do with the fact that the star is moving so fast. The motion of an object can change the waves it is emitting. This phenomenon is known as the Doppler effect. A common example of this is an ambulance speeding past you. When the ambulance is speeding towards you, its sirens sound higher pitched, and as it drives past you and is moving away, the sirens will sound lower pitched. An object moving quickly towards you causes emitted waves to compress, leading to smaller wavelengths. In contrast, an object moving quickly away from you causes emitted waves to expand, leading to larger wavelengths. The Doppler effect is applicable to all waves, including light. When an object is moving quickly towards the Earth, the light it is emitting is compressed, creating a shorter wavelength and thus making the light appear more blue. This is called blue shift. When an object is moving quickly away from the Earth, the light of the object it is emitting expands, creating larger wavelengths and making the light appear more red. This is called a redshift. Redshift is a tame side effect of our understanding of relativity, but what happens when the universe pushes relativity to its extremes? A phenomenon known as gravitational lensing is the direct result of massive objects warping spacetime. As light from a distant object, such as a galaxy, travels through space, sometimes it encounters something massive, for example, a black hole. Provided the light can escape the extreme gravitational field of the black hole, it will bend, distorting the image of the light behind the massive object. This allows us to use elements of general relativity to locate massive objects within the universe.